Next week when we come back, we will be onto the second lecture. Okay, the first lecture is about sampling. And what is sampling? Sampling is to make a conversion from continuous time to discrete time, right? So now in this next lecture, we are going to work on the opposite direction. How do we convert from discrete time samples back to the continuous time domain? And I argue that we will see you can treat it as some kind of interpolation by the name of Sinc, S-I-N-C, Sinc, okay? Sinc interpolation. So let's take a preview. So in the next lecture, we are going to start again from the last same equation. This is a sampling effect, right? In the frequency domain, we get shifted copies of spectrum. They all add together. So you want to make sure that we sample at sufficiently high rate, 2 times the bandwidth, then we should be fine. We should be able to uniquely determine a continuous time signal. But how? In this lecture, we calculate. We will just go into more detail in the next lecture. Okay, so you will be able to work out together everything about that low pass filter, basically. So we're going to first consider this low pass filter that's a frequency response. Okay, that's a frequency response of a system. So when we talk about in this course, and probably you have learned it from signals and systems, when we talk about applying a system, we mean convolution in time. Linear time invariant system, right? Linear and time invariant systems can be characterized by their impulse response, their response to the delta function in continuous time or discrete time. So we are going to look at this desired frequency response. This low pass filter is ideal with a perfect cutoff right at Nyquist. Let's put aside whether or not this is possible in practice. Okay, but an ideal filter for this frequency response, we can calculate the corresponding impulse response. We can calculate the impulse response by applying inverse Fourier transform. Okay, so we are going to apply inverse Fourier transform to this desired low-pass response in the frequency from frequency to time. And then the result is a Sinc function. Okay, and the result turns out that we will next week when we come back, we'll work it out. We'll work out that we will begin with this ideal low-pass filter with constant gain, which turns out to be t, and 0 after the cutoff frequency. Okay, constant within the cutoff frequency and 0 outside. That's the ideal low-pass filter. And from here, we are going to work out. We are going to work out the impulse response h of t by applying what? By applying inverse Fourier transform. And we know that by convolution theorem, a multiplication in frequency is equivalent to convolution in time. Okay, we're going to multiply our sample signal with the ideal response to keep only the middle part. That's a key idea. Okay? Keep only the middle part by applying the low-pass filter, which is equivalent to taking convolution in the time domain. Take convolution of our sample signal with the h of t right there, with the inverse Fourier transform of this ideal response. So turns out that, let me just show you the result. This is the definition of inverse Fourier transform for continuous time. Okay, there's a factor of 1 over 2 pi and summation, no, not summation, integration, 积分了. Integration from -infinity to infinity. And we take the spectrum, multiply them by complex exponential, and just integrate everything together to go back to the time domain. It turns out that it's rather straightforward. With a few steps, you will be able to show that the result looks like that. Looks like that. And we'll, so next time when we meet, we will make a sketch for that. And we'll define that. We'll officially call this function the Sinc function. Okay, we can define Sinc function by sine theta divided by theta. Okay, that's a result of our ideal low-pass filter. That is its impulse response in the time domain. Okay, yeah. So impulse response is the Sinc function. But then the key issue is then now we need to imagine what will happen when we convolve this Sinc function with our signal after sampling. Okay, so let me just for the last time today recall that this is our signal and this is the signal after sampling. Now it consists of delta spikes, right, with modulated height according to the signal's amplitude. So that's our result. We are going to basically convolve these spikes, the series of spikes, with this signal over here, with this. That's the impulse response. That's the function we need to use to convolve with our sampled signal. Okay, so we work it out next time when we meet. Okay, so if you draw a Sinc function, it might look like there's the middle part, and then it goes it goes positive and negative, yeah, something like that. So we'll study how this signal is going to convolve with that, and how do we interpret and argue that this is a process of interpolation. 内插 in Chinese, interpolation is 内插 So we argue that this can be regarded as nothing but just interpolation. Just interpolation, that we'll figure it out. Okay, so I guess I can finish a bit early. All right, so I'll stay here for a while. Thank you for being here. See you next week. Welcome back to DSP. So today is our second week of lecture, and we will have a first discussion session tomorrow. Okay, tomorrow we have the first discussion session, and please notice that I've posted homework number 1. Okay, homework number 1 is you can download it from EE class, and there are going to be 3 questions. So I've asked my TAs to help creating a sign-up sheet online. Okay, sign up. Yeah. So you will need to answer. So please look at the 3 questions right here. And if you're interested in volunteering to be showing your solution on the stage, please sign up. Okay, please make sure that you receive the notification from the TAs, and you'll need to sign up. And we will have, as I promised, we will have an English session as well as a Chinese session, Mandarin session. Okay, 国语 Yeah. So any question regarding that? Regarding what's going to happen tomorrow? And yes, please. Yeah. Yeah. So the question is, can I select one session to attend? The answer is yes. You don't need to show up both. You are welcome to stay if you choose to first attend the English session first. Yeah. Is that clear? Yeah. 怎么样？ The question is, if I sign up for both Chinese and English, does the probability increase 2 times? You're welcome to do so. I cannot promise. I taught probability before. I need to calculate. I need to talk to my TAs. Yeah. But the short answer might be yes. This is the first ever discussion session, right? So we are not going to spend time to make sure that we exclude your, come on. We're not going to be so careful. but you're welcome to try to sign up for both. But please show up, right? Okay. But another question might be, do we announce who are selected beforehand? Last year, is Jason here? Because Jason is one of the TAs who took this class last year when he was an undergraduate. 他在隔壁是 Yeah. So we'll figure out, will we announce the result of random selection before we meet, or will we not? I'm not sure. I think last year we didn't announce. We just you just come into the classroom and the TAs will write down the ID number. 学号写黑板上了啊。That's a moment. 啊？哦，上课前会公布的。Okay, so the answer is we will announce it. Okay, so you can make sure whether or not you are selected. Okay, yeah. But let me just quickly tell you that there are 3 questions. Okay, the first 2 questions will use DTFT, the discrete-time Fourier transform, but we haven't officially introduced it yet. It will happen today. But I am here, so I'm assuming that if you have taken signals and systems, this is not new to you, okay? Discrete-time Fourier transform. So the first question will ask you to derive the DTFT of a time domain signal in discrete time, okay? So that's just calculation. You do need to use the definition of DTFT. So if you want to work on it as early as you can, you might need to refer to the textbook or to signals and systems. Okay, so that's the first question. The second question is the opposite. I asked you here to calculate the inverse DTFT of a spectrum. So you're given a spectrum or a frequency response. And I asked you, this is something similar to a low-pass filter, but not quite, not exactly. But here I asked you to calculate the inverse Fourier transform. So basically to go from frequency domain back to the time domain. Yeah, using the inverse of DTFT. So those are the first 2 questions. But otherwise, the third question is related to today's lecture for sure. It's about interpolation. So later we are going to show that the ideal way to convert discrete time back to continuous time is to perform a kind of interpolation by the name Sinc, the Sinc interpolation, S-I-N-C, Sinc. Okay, the Sinc interpolation. But here I designed a problem where you are going to study not Sinc, but simply linear interpolation. Now, linear interpolation has been done a lot, right? A lot of time we use linear interpolation to explain things. Okay, so it's a very natural way to process a signal, but here we want to argue that linear interpolation might introduce some spectral distortion. Okay, so it's not recommended. You can do that, but it's not recommended. So those are the 3 questions that we're going to discuss tomorrow. Right? So with that, let me just switch back to the. Thanks for the questions. Yeah, help clarifying things. And so let's just go back to the lecture slides. Right? Right. Okay, so let's start lecture number 2, D to C conversion. And we treat it as a kind of interpolation, Sinc interpolation. So here is a bit of recap. So just let's restart this slowly. So we have the beginning point really is a signal in the time domain, in the continuous time domain. Okay, yeah, continuous time domain with a continuous time variable t, right? And we argue that when we sample it with a sampling period, so essentially what's been done is to convert the signal into a train of spikes, a sequence of spikes. And we call the result x after sampling, small x. Yeah. Where's the eraser? Huh? We call the result after sampling to be, rename it x sub s of t, and it's defined as the signal of our interest times something we called s of t, where s of t is just a infinite sequence of delta function with the same height 1, okay, and summation over all n, all integer n, okay. So that's a definition of the function, the s of t right there. And so now we consider, so last week we spent some time to calculate, to convince us that the Fourier transform of the result, when we multiply 2 signals, these 2 signals in the continuous time, and we take the Fourier transform, the result is going to be a spectrum denoted as big X. And turns out that it will be equal to an infinite summation over this index K, and it's going to be the original spectrum, but shifted to the right and to the left. Omega minus n times, K times, not n times, K times omega sampling rate, essentially. And there is also a normalization factor, a scaling factor, I should say, a scaling factor that's simply there. So that's the correct way. And we show that, so that's like what it looks like in an equation. But last time we also showed that we want to make a sketch, make a drawing, right? Make a drawing. So what's happening is that if we just make a sketch of this, what's happening here in the frequency domain, and we very soon realize that as long as our signal is band limited to begin with, we assume that the bandwidth is, do I have a bandwidth right here? If the bandwidth is 2 pi times b. So always be careful that here, sometimes when we talk about bandwidth, the unit matters. So here the unit, I'm assuming the big omega, right? Big omega has a unit of radian per second, which is 2 pi times hertz, okay? 2 pi times hertz. So I say a bandwidth b in hertz, then as long so the criterion is that as long as the sampling rate is at least 2 times higher than b in hertz, then we are then we are pretty good. Okay? So that is to say, what will happen after sampling is a infinite summation of the spectrum to the right, shifted to the right and to the left. Okay? So as long as our sampling rate here, omega s, equals to 2 pi, which equals to 2 pi sampling rate. As long as it's bigger than 2 pi p, 2 pi b, bigger than 2 times 2 pi b, then these shifted copies are not going to overlap. And we like it, right? And we like it because the spectral shape is not going to be changed. The spectral shape is preserved, 是保持住的. So we're happy about that. So we like it. Also, on the negative frequency side, we have everything is symmetric. So let me just draw another one copy. But conceptually, these the summation extends to both directions. Okay. Very good about this. So we also, and this is good because, so now the question is, how do we go back from the sequence of spikes back to the continuous time? We want a reconstruction. 我们希望重建. We want a reconstruction from the spikes. The spikes now is already a lot is missing. Everything in between spikes, everything here is missing. Everything here in time is missing. So we need to reconstruct. 要重建起来. We need to construct it, get it back. Right. So the question is, how do we get back the continuous time, a copy of a reconstructed signal, so that the reconstructed signal will be the same as the signal before sampling? Okay. So let's talk about frequency domain operation first. Okay. So this is what's recommended. We recommend that we can introduce low pass filtering. We can introduce low pass filtering in the frequency domain. That is to say, we multiply. I suggest that we multiply the entire extended spectrum with the yellow thing right here, 黄色, the yellow thing right here. Okay? So the yellow thing right here is a low pass filter. Low pass filter, so that we want to only keep the middle copy while rejecting everything else. Because the middle part here is what we begin with, right? The original band-limited spectrum. So we want to keep only the middle part while rejecting everything else. Rejecting all the extra copies of the spectrums which are sifted elsewhere. We want to reject all those high-frequency components while keeping only the middle part. So this is a low-pass filter, and we want the low-pass filter to introduce no spectral distortion. That is to say that the gain here needs to be constant, so that there's no distortion. The gain here has no distortion, while in the stop band everything is 0. Okay, so that's an ideal case. So that we call this frequency response an ideal low-pass filter. So do I have the equation right here? So let's try to read the text right here. So conceptually, we use a low-pass filter for reconstruction. Reconstruction from what? From the samples. From the samples back to the continuous time. As long as the sampling rate, still we need to emphasize this. We can do that, and we are guaranteed to have a perfect reconstruction only if the signal has a finite bandwidth to begin with, and we sample it at least 2 times higher, at a rate that is two times higher. Okay? But with that, then in this lecture, we're going to look at more details about this low pass, and in particular, we calculate the inverse Fourier transform of the low pass response. Okay? We go from here is in the frequency domain, but we go back to the time domain. Okay? So to do that, we need to calculate the impulse response of this reconstruction filter. And later we point out that we have an interpretation, 有个诠释一个角度啊。The way we look at what's going on here in the time domain is that we point out that this low-pass filtering actually corresponds to interpolation. 中文叫内插 interpolation is nothing but interpolation. So why is that the case? First, we need to show write down the frequency response for the low-pass filter. Okay, so here that's the next slide. So we recommend that in this low-pass filter, which I'm going to denote as H, here's the frequency response. So let's be specific. So H, as I said, should be constant in the passband and 0 elsewhere. 0 outside, constant when the frequency is below pi times sampling frequency. That is the Nyquist rate. Because 2 pi times that is the sampling rate in radian per second. So pi times that is 1/2, right? So here, I'm suggesting that the cutoff frequency right here really is pi times sampling rate, which is half of that. Okay? We recommend that we define a ideal low-pass filter with a cutoff. This is called the cutoff. The cutoff frequency in radian per second is pi times the sampling frequency. That also corresponds to the Nyquist rate. Sometimes we call half the sampling rate Nyquist. It goes by the name Nyquist, or this Nyquist rate. Nyquist rate in radian per second. Okay? So with that, this definition and the gain here, it happens that we recommend the gain to be exactly t being the sampling period. Okay? All right, so from this, is that clear, the definition? Okay, low-pass filter with constant gain t. But why t? Why t? The reason is because when we multiply our frequency response with this thing right here, when we multiply, we take the product of the sample spectrum, the spectrum after sampling, with the frequency response, then just by looking at the equations, you should be able to figure out what will happen. You should be able to figure out that what we get is exactly just the middle part, and we have the right scaling factor right there. Okay, this a long story short, t. This t right here cancels with this 1/t. right? There's 1 over t right here. Is that clear? 1 over t right here and here, if the gain is t, then the two of them, when we take the product, the result is 1. Okay, so that's one tiny detail. It's not the most important, but here is my explanation why the scaling factor is t right here. Okay, because this t will cancel with the factor here, 1 over t. Okay, and what's remaining is really the middle part with the right shape, no distortion, and the right amplitude everywhere. Okay, is that clear? Right magnitude everywhere. 那个正负是对的啊。The magnitude will be right at every frequency. Okay, is that good? Yeah. Should be able to notice that either from drawing or from the equation, we will be able to figure out that, sure, it should be clear that when we multiply a low-pass filter, we keep only the middle part, which is the original spectrum. Keeping only the middle part. That's the idea. Okay, so if we just move on to the second point right here, so this is what we call filtering. I need to emphasize, okay, at least to my in my career, when I say filtering, it's a multiplication in the frequency domain and convolution in the time domain. Almost always, okay? So that's technically the term, what it means in signal processing, in the signal processing lecture. I'm not sure in other field, you filter coffee, is it a low-pass filtering? Yeah, no, I'm not sure. But in signal processing, filtering, 滤波, it always means to multiply our spectrum with a frequency response. Just nothing more, nothing less, multiplication. In the frequency domain, that's the definition of filtering. Can we agree on that? Okay? Can you agree on that? When we say filtering, is a multiplication in frequency. Sometimes in certain applications, we also multiply a signal in time with another envelope in time. Multiplication in time domain, sure, you can do that, but let's not call it filtering. Let's call it something else. But when we say filtering, it's a multiplication in the frequency domain, which corresponds to convolution in the time domain by a theorem. Okay, there is this convolution theorem which tells us that we can achieve filtering by convolving one of them with the other. Okay, so here the idea is to convolve our result of sampling with the impulse response, what we call an impulse response. Impulse response, and what is the impulse response? The impulse response is the inverse Fourier transform of the frequency response. So that's how we call them. So the impulse response, small h and big H, they form a Fourier transform pair. One in time domain, the other in frequency domain. They form a Fourier transform pair, 一个对偶, a pair. Right. So impulse response is the inverse Fourier transform of H, of big H, which is defined right here as a constant in the pass band, 0 in the stop band. Is that clear? So far, so good? So about all the terminologies right here, we want to make sure that we agree on all the terminologies. All right, so but with that, the next question, what's the next question? The next question is now we are ready to do the calculation. Okay, we're ready to derive the inverse Fourier transform. Make the calculation. Let's do the calculation next. Okay, let's calculate together what's the inverse Fourier transform of this thing, the big H. Okay, because it's important. So next thing, let's do this together. Probably over there. Okay, so we are going to calculate the inverse Fourier transform of the desired frequency response. Okay, so here in the middle, I use some like bluish color right here to indicate a mathematical formula that we introduced for the first time. Okay, you can also find it on the textbook for sure, but here I want to just introduce that the inverse Fourier transform can be calculated this way. So here we have the desired response, and we need to go to the time domain. And the way we do that is to consider this as the gain to a small wavelet at exactly the frequency, the corresponding frequency. And then we are going to collect everything together by integration. Okay? This is a gain which will happen to any selected signal at this frequency, any signal at this exact frequency, so that when we collect everything in the frequency domain, we do an integration from -infinity to infinity. All the frequency are going to be collected together, okay, using this idea. Okay? And there is also a factor 2 pi that should not be missed. Okay, is simply there. So that's the inverse Fourier transform. Sometimes we can also use this notation with a script f, 草写的, the script f to denote Fourier transform. And with the -1, that's the inverse, right? Inverse Fourier transform. Inverse Fourier transform of any given spectrum is defined. Okay, I'm running out of space. It's defined as 1/2 pi times the integral. 1/2 pi times the integral. And we need to get the result. Just to jump to the conclusion, it turns out that when we plug in h right there, you will get the result right here. Okay, so let's do it together. Okay, let's spend some time to do it together. Okay, so 1/2 pi, we are going to do it together. So first of all, what is h? H is constant, right? H is constant, so the constant is what? The constant is t. So t times e j omega t, and the integration is with respect to big omega. But h is t only in the passband, right? Only in the passband. So that now the lower bound, lower and upper bound for integration should be from the cutoff frequency within the cutoff within that bandwidth. Okay, so the integration should happen from minus pi sampling rate to pi times sampling rate. Yeah. Minus pi sampling rate to plus pi sampling rate. Okay, so next we can just organize everything a little bit. Here's t, there's 2 pi, and now this is pretty simple. This is simply exponential. So in exponential, we know how to do the integration, right? So let's just be careful. I want to be careful. So here is jt 1 over that, and e j omega t with omega lower starting frequency right here, ending final frequency right there. Okay, that's just integration. Antiderivative. That's a term I'm missing. 反导数. Just to figure out the antiderivative of this function. Right? In the integrand here, we are integrating with respect to big omega, not t. Okay, so let's just be careful. That's why we pull out this constant, jt, right here, shows up right here. The factor shows up right here because we're finding an antiderivative, 反导数, antiderivative. So far, so good. So now let's just push up forward one more step. T still here, 2 pi still here, jt is still there. But now here we mean exponential j pi sampling frequency t minus exponential j this frequency times t. Yeah? Okay? Minus exponential j that frequency t, and we close the parenthesis. Yeah, okay, so yeah. So here, for those of you that know, just by applying Euler's formula, what is Ej something? Ej something is cosine that thing plus j sine that thing, right? Yeah. So when you just subtract the two of them, what you get is 2j times sine of that thing over there on the exponent. 在那个指数的地方 exponent. Okay? Pi fs t. Okay, so hopefully so far I'm still correct. Okay, so now what's going on? So we have t over 2 pi still here. Jt is still there, but on top now we have 2j sine pi times sampling frequency times t, which is a function of t, right? The inverse Fourier transform is a function of t, okay? Small t. So now we are almost there, almost there. So just cancel j, cancel 2, right? So now what do we have? Now we have sine pi times sampling frequency. What is sampling frequency? Sampling frequency is by definition 1 over t, right? 1 over t. So here really we have divided by big T, and just be careful, multiplied by t, okay? Divided by what? At the bottom we have exactly the same thing, pi here. If we just move the big T right here to the bottom of bottom, to the denominator, 在分母的地方啊。The denominator, then finally we get this expression. Isn't that the same as here? Yeah, it's the same. So that's the way I make the derivation, right? A function of t. That's what we get back in the time domain. Okay. So far so good. Yeah. So that's a simple exercise, hopefully. And now, so here. We also, I love drawing sketches, yeah, because I learn things by drawing. So now you're sure we have this beautiful thing, sine of something divided by that thing, and but how does it look like in the time domain, right? How does it look like in the time domain? Yeah, how does it look like in the time domain? Maybe I can erase this part. So next thing. We want to be careful to draw a sketch, right? To draw a sketch. So now h of t is sine of pi t divided by big T divided by the thing, same thing, pi t divided by big T. But let me mention that here we have a small problem. We have a small problem because when t approaches 0, when t is 0, this expression is not defined, right? You notice that when t is 0, we have a 0 at the denominator, and we cannot divide things by 0, right? So I need a suggestion. What do we do? Can we apply L'Hopital's rule? 罗必塔法则好不好啊 L'Hopital rule, anybody? When t is 0, let's define. This is when t not equals to 0. So when t is 0, let's apply L'Hopital's rule. L'Hopital. Yeah, you can apply L'Hopital's rule, or yeah, it's not necessary you need to do that, but let's define that when we apply L'Hopital's rule, because the sign of something equal to that thing when that thing is very small, right? When that thing is approaching 0. So let's define this to be 1 at t exactly 0. So here, this is why we're going to try to make a sketch. Okay, we try to make a sketch right here. Yeah, but you know what I mean. Okay, it's gonna be 1 at time equals when time equals to 0. Okay, so we already got that. So 1 when time equals to 0. And the next thing is to realize that what? To make a sketch, we should expect h of t to approach something when t approaches infinity. H of t should approach 0 when t approaches infinity. Can you agree on that? Yeah. Because simply t is right here, right? Sign is bounded. Sign is bounded, right? So when t approaches infinity, we should expect to see an envelope like that. An envelope also in the negative part. And this is an even function, 左右对称, an even function. It has an even symmetry. Right. So so with that envelope and 1 at time 0. So next thing is to figure out there are going to be 0 crossings of h of t in h of t. H of t is going to cross 0 horizontal infinitely many times, okay, because there is a sign component on top, right? So it's going to alternate sign. So every multiple of t is going to change its sign. So in the first t right here, it's going to go to 0. And then it's going to cross and change polarity and then go back to 0 at 2t. And at 3t, we expect it to again come to 0. And let me draw 4t and so on. While the envelope, the amplitude is going to be, should I say, attenuating, okay, as t approaches infinity. So that's on one side. On the other side, we have exactly the same thing. H of t turns out to be an even function, okay? So let's just, for the sake of completeness, minus t, minus 2t, and so on. We expect the signal, when we draw sketch, goes negative and then positive, crossing 0 at integer multiple of t, and so on. So that's a simple sketch. You can do it by yourself, right? So that's how this impulse response looks like. Okay, so from now, by now we have completed the derivation as well as making a sketch. Okay, so far so good? So far so good. And what are we doing right here? Why do we take this calculation? Because this is an impulse response, right? And we are going to use it. How do we use it? We are going to use this impulse response and convolve it with a sequence of spikes. That's what we're going to do. Okay, we're going to do, because the purpose, there's a purpose. The purpose was to make a D to C conversions to reconstruct the signal back in continuous time. Okay, let's be reminded. Let's remind ourselves that's the purpose. Okay, so in the middle step, we need to figure out that this is the h of t that we're going to use for convolution. So next thing we're going to study what will happen when we convolve this Sinc function with a sequence of spikes. Okay, yeah, with any arbitrary sequence of spikes. Right? So a few remarks right here. As I mentioned, the function sine theta divided by theta is often called and denoted as the Sinc function, Sinc. So we write Sinc of theta. We really can, you feel free to do this. Okay, feel free to do this. But be careful that we also need to define the function at time 0. Okay, so let's define Sinc function at 0 to be 1. Okay, and it also so to make everything continuous. So now this Sinc function is also continuous in time. And by the previous slide, we show that h of t now in this notation is simply Sinc of what? Sinc of pi t divided by big T. Okay? And now we use the notations. H of Sinc. And now our task right here, the next task I would like to invite you to do is to make a sketch of convolution. Okay, make a sketch of convolution, and convolution of what? Convolution between two things. Okay, we're going to convolve H with the result of sampling. What's the result of sampling? The result of sampling is to multiply our signal of interest with the spike train, with the delta function, the spike train right here. Okay, yeah. So what is going to happen? What's going to happen? Yeah, so I do have a highlight, okay? But I may need to use the board right here, okay? So let me erase this. So here now, next, let's draw another sketch. Now in this sketch, we are going to visualize. We're going to visualize convolution of exactly these two things. The first thing is the spike train. Which has been the result of sampling a continuous time signal with a fixed period. Right? We sample the continuous time signal with a fixed. I'm not doing a very good job right here, but with a fixed period, you know what I mean. In continuous time. So now this is what we denote as here. Okay, multiplying the continuous time signal with the spike train, and the result is denoted as x sub s. Okay. So let me say this is x sub s, and the continuous time signal here, original signal has been denoted as x sub c, emphasizing that it's continuous. Okay, emphasizing that it is continuous. And S stands for sampling. After sampling, before sampling, simply put. Okay, now. All right, so now we want to visualize what's going on when we convolve this with H. What is H? H is Sinc. Okay, yeah, H is Sinc. So first, I have this suggestion. Okay, I do have a suggestion right here. So I suggest that sure, x of s is by definition the multiplication of xc with the spike train. But there's another way to write, to express x sub s. There's another way to express x sub s. How? So here's my suggestion. You might want to realize that the other way which is also correct, is to consider summation n on the outside, but inside we have x n times delta n minus, no, not n, t minus n times big T. So that's my recommended way of writing it. Okay, my recommended way of writing, and you can check if this is correct. And I claim that this is also equivalent. This is equivalent. Why? Because the height of each spike, if you take one spike, each spike has the height, 那个高度 has the height. How tall is it? It's exactly so tall, right? xn. For example, if this is time 0, then this is the height of this spike is x0. And if this is t, then the height of this spike is x1. And so on. So if the height of this is n, if this is time n times big T, the height here is x of n, and so on. Because that's how we define sampling. Sampling is to evaluate the signal at integer multiples of t, right? And this is how we denote the result, right? Because this is correct because x of n has been defined as x of c evaluate at integer times big T, n being integer. So this is another correct way of thinking about the, yes? Right. So here I need to be, So the question is whether I should write down n or nt. Is that your question? Yeah. So I think I'm using this notation. Okay. When we look at the continuous time signal, which is denoted by x sub c. Okay. So x big N with bracket, 中括弧, bracket. When we use the bracket, then what's inside here can only be integers. That's a very good question. Let's clarify our notation. It could be confusing. Yeah, I agree it could be confusing. But when we use the bracket, use 这个中括弧, when we use the bracket instead of parentheses, 小括弧, or parentheses, when we use the bracket, then the inside is a discrete time index, which we assume in the textbook, the authors assume that this n really is an integer and nothing else. You cannot plug in x bracket 1.5. That's not allowed. That's not even allowed. So that's why here I just use n instead of nt. Whereas you're sure x of n stands for xc at nt. For sure, you are correct. You are right about that, on that. Okay, is that clear? Does that answer your question? Right. So I really like this expression because it allows us to see. It emphasizes that the result of sampling is going to be a sequence of spikes, each having this height, each having a different height. And we just collect the height, record the height, and call it a sequence of numbers. That's what's happening in sampling, when we convert the signal from continuous to discrete time. So I really like this expression. It's just spikes shifted to the right and to the left, but and modulated by the height, which has been sampled, okay, which has been measured. So I like this expression. Both are correct, but we are going to rely on this expression in the following derivation. Okay, so can we agree on that? That this is also the correct. This is also a correct expression for what's going on after sampling. Okay, it's also a correct. Yes. No. Okay, so the question is, should we put nt here or simply small t? Okay, so the reason I put small t is to emphasize that the entire thing here should be considered as a function of time for any t as a real number. So here t is still continuous, but here the tricky thing is that here n is discrete. So that may take a while. That may take a while to understand our notation. Here we emphasize that this is a continuous time signal, even though it's almost zero almost everywhere. Even though that is zero in between, but in between here you can still talk about x sub s. It's simply zero, right there. But in here we cannot talk about x of anything fractional. 不能讲小数点，不能 n. You cannot take n being a non-integer. That's not allowed inside a square bracket. But inside the parentheses, everything is still considered as continuous time. So that's a difference in notation. Okay, did that answer your question? Thanks for the question. Okay, any other question right here? Any question from the back of the classroom? Okay, you can always come to me after class, right? So, but here is a nice distinction of our notation: continuous time, discrete time. But everything is put together with either this expression or that expression. Okay? The emphasis is different, okay? But we are talking about the same thing. So now we can finally consider using this expression, and we are going to make a substitute that into convolution. Okay. So now we are going to study what will happen when we convolve. Let's call the result X reconstruction because that's our purpose. Our purpose is for reconstruction. R is going to be defined as we take our signal after sampling and convolve it with h of t. But then what is here? Here we are going to use this expression, okay, to substitute. 代入, substitute. Well, summation n, x bracket n delta of t continuous time, t minus n times sampling rate, no, sampling period. We're going to convolve this with h of t. And next, let's put ht inside. And we can do that because convolution is linear. Right? Because convolution is linear, we can put h inside. So we're going to put h inside. So we have xn delta of n, t minus n period convolve h of t. And I'm going to here put the parenthesis in here. Put the parenthesis in here. Because as far as convolution is concerned, x of n is nothing but a scaling factor. And again, because convolution is linear, so I can put the bracket around right here. Yeah? Now we're almost done. Okay, we can almost take a break. Yeah. So this is just nothing but reorganizing the summation and convolution. And because everything's linear, you can make some arrangement. 会做一些调整啊. You can make some arrangement because everything's linear right here. And does this look familiar? There's something that we can apply right here. When we convolve a signal with delta shifted to the right by so much, what's happening? We shift that signal, correct? We shift that signal exactly the same amount. Okay, so result now, finally, the result we get, okay, here, the result that I want is this expression, and we will take a break. Okay, the result I want here really is h evaluated t minus n times sampling period and summation over O n. So we'll take a break and we make a sketch after the break, right? Now.